Hi, good afternoon, everybody. It's a pleasure to be here. So, as I was introduced, Vishal, Shete, Managing Director at Terra Quantum. We have about 200 people globally, and there's three parts to our business: algorithms, compute, and security. Algorithms is the most commercially active side of our business. In compute, we do R&D, and we've got a cybersecurity business as well. Today, I'll be talking just about algorithms. In fact, I want to start today's discussion by thinking back to 2011, when Mark Andreessen said, "Software is eating the world." He was referring to the exponential growth that was happening in Silicon Valley at the time, in terms of software innovation that was driving value, with the likes of Facebook and Instagram and Twitter growing and exploding in that time. Since then, we've seen how much value has been added to business and society by the growth of these companies, these software innovation companies. And we've seen this actually, this trend actually accelerate with the emergence of AI and the adoption of AI as well. So in this context, I wanted to frame the question, in a world where software eats the world, what is the role of quantum? Particularly, I'd like to look at what is the role of quantum software. So what is quantum software, and what is software in the first place? So software essentially can be defined as a set of instructions that help a computational device process, store and process information. There's different levels of abstraction of this, starting from assembly language through to higher level languages, and then you've got low code and no code these days. We've seen how software has had this exponential growth as we were just talking about and has been referred to today as well. But what is the future of this? Do we just see incremental improvement with AI, or will we have a step change at some point? So in this context, quantum software is essentially instructions that allow a quantum circuit to store and process information. And what is a quantum circuit? A quantum circuit is essentially a collection of qubits and gates that allow the imposition of certain properties of quantum mechanics, such as superposition and entanglement. So quantum software, with the use of these properties of superposition and entanglement executed on some of the hardware devices that we've been talking about today, can create exponential improvement in computational possibilities. It can solve problems that we can't even imagine, as we've been talking about, can solve encryption, and do these amazing magical things. However, as has also been addressed today, this hardware, so that the device that is manipulated by this set of instructions, is still maturing. It's not reached its full state of maturity yet, and we can't today handle large-scale quantum circuits. So one might ask, in this context, why bother with quantum software? Especially from a corporate perspective, why bother with this? Let the academics and the researchers figure it out. When it's mature, then look at corporate adoption. That's a very, very interesting question, and in fact, I think one that many people struggle with. Why bother with this? Why bother with quantum software especially? Well, here's the thing. We at Terra Quantum, we've been looking at two ways of addressing this quandary. Firstly is in an area of quantum machine learning. So in quantum machine learning, what we've done is we've kind of found a way to make use of smaller quantum circuits that can fit in the devices that exist today, and get those quantum circuits integrated into larger machine learning architectures. So we introduce an element of novelty, an element of non-determinism to improve the learning capacity of the overall architecture. That's quantum machine learning. But what I wanted to focus on today was the other angle, where we are looking at how we're creating improvement with quantum software, which is on tensor networks. So tensor networks were created in quantum physics. They were created to understand and study the behavior of quantum particles, understand the interactions and correlations of these quantum particles in quantum physics. As Jan referred to earlier, this problem is so complex that it was one of the reasons Richard Feynman talked about inventing a quantum computer in the first place. Tensor networks help us address that problem by providing a framework to understand the complexity, the exponential complexity of the quantum mechanical world. These tensor networks can be thought of, we know neural networks of today, right? Neural networks we know and love. they're a software representation of intelligence, software representation of our brain. Similarly, tensor networks can be seen as a software representation of the language of quantum mechanics. And at Terra Quantum, and at other places as well, we're using this software approach to solve some of the most complex problems in the world. So what we do in particular in this space is look at problems in high dimensions. Tensor networks are very good at dealing with problems in higher dimensions. So these tensor networks basically deal with problems in higher dimensions, and they are, because they're from the world of quantum physics and quantum mechanics, they're bilingual in a way. They can speak to the classical compute, and they can speak to the quantum compute. They can be executed on both. And that we see as the primary reason to use quantum and develop quantum software using this technique today, because you can generate some of that possibility, but not the full possibility of a full-scale fault-tolerant quantum computer, of course. Otherwise, there'd be no reason to build the hardware. But you can create a software-based representation of things like entanglement and solve problems which are beyond the reach of other approaches. So what does this mean, right? So what type of problems do we solve with tensor networks? So with something like tensor networks, we break the curse of dimensionality. So the curse of dimensionality refers to a mathematical concept where when you have a problem with additional dimensions, the processing complexity and time increases exponentially. So there are many problems in business and society, and I'll go into a couple of those, which have this characteristic. So as the problem gets more and more dimensions, the processing time and complexity explodes. Tensor networks are very good at dealing with this increase in dimensions. They're very good at dealing with these increase in complexity. And by doing this, we are able to break this curse of dimensionality and handle this additional complexity that comes with it. So what are some of the examples of where we're applying this? One example is in molecular modeling. Molecular modeling is a very famous application. In fact, our friends at DeepMind and Google have been looking at molecular modeling for quite a while. In fact, DeepMind, based right here in London, created this very famous application called AlphaFold. We made a lot of headlines for it, and rightly so, which essentially predicted the 3D structure of a molecule given its genomic sequence. And that created a lot of headlines. It is incredibly helpful. By understanding the 3D structure of molecules, what we're able to do is better understand biology and chemistry. In fact, molecular modeling is one of the most famous problems in computational biology and computational chemistry. While AlphaFold has done this amazing job, what it is dependent on is training data. So to run that, you need training data based on crystal structures or crystallized molecules which are needed to train the algorithm. However, not all types of molecules can be crystallized. So you will never have enough training data for this application to work. What we do in this space is we do the calculation. We don't do the prediction, we do the calculation based on empirical and semi-empirical methods of how this molecule looks in 3 dimensions and behaves in 3 dimensions. So you have an understanding of yourselves and different drugs and how they can attach to this and how they can help inhibit things. And that is the power of molecular modeling. And just to give you an example of how much the improvement that's possible with our approach, we have the comparison here against CREST, which is seen as a gold standard. And you can see with the tensor networks approach, a 10x to 100x speed up in doing this calculation. So between 10 to 100 times faster than the best alternative approach to solving this problem of understanding the 3D structure of a molecule. One more example, which I wanted to touch on really briefly, was in the space of options pricing in derivative markets. So in financial markets, the most complex process, the most computationally heavy process in financial markets is Monte Carlo simulation. Monte Carlo simulation is used to understand what are the future states of the world, and as a result of that evolution, what is the price, or what is the risk to my financial product, and therefore what is the price of this product. we're able to speed up Monte Carlo simulation quite significantly as well, which means you are able to get to the price of your complex financial instrument a lot faster, up to 5x or 10x faster than the best alternative approach, which uses Monte Carlo simulation. So what does that mean? That means as someone managing a trading desk, which is trading derivatives, I'll get to understand my risk a lot faster and a lot better. So which means I won't be in a situation where the markets has moved against me and I don't know about it and I'm not able to react with risk mitigation procedures. So we started the discussion today looking at Mark Andreessen talking about why software is eating the world. And Jensen Huang, about 6 years later, talked about AI is eating software. I hope today you've had a bit of a glimpse on how quantum software could be the next paradigm shift in this evolution. I hope you've had a bit of a glimpse on how this quantum software could be a catalyst for the next round of innovation which can help business and society around the world. Thank you and look forward to the discussion.